We will now study sets. So a set is simply a collection of elements. And you should have studied sets in a previous course. So if A and B are two sets, then A is called a subset of B, which is written this form, if and only if every element of A is also an element of B. We'll say that A is a proper subset of B, which is written this way, if and only if A is a subset of B, but there's at least one element in B that is not in A. If we're given n sets A1 through AN, the Cartesian product of them is A1 cross A2, blah, 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 blah. It's the set of all n tuples, ordered tuples, A1, A2 through AN, such that A1 is in the set A1, A2 is in the set A2, so on and so forth. So let's take a look here. We have A is the set 1, B is the set of 1, and the set 1. Is A a subset of B, and is A a proper subset of B? Well, we take a look, right? B contains 1, and since 1's the only element in A, every element of A is also an element of B. So yes, A is a subset of B. Is it proper? Well, again, if we take a look, B has the set 1, which is not in A. So not only is A a subset of B, but B has an element that A does not. So yes, A is a proper subset of B. Alright, so we have the terminology down. Now we can start looking at proving properties. So this is a new type of proof. It's called the element argument. And this is the basic method for proving that one set is a subset of another. So let sets x and y be given. Prove that x is a subset of y. We suppose that x is a particular but arbitrarily chosen element of x. And then show that x is also an element of y. So we take a look at these two sets here. So A is the set of all integers m such that m is 6r plus 12 for some integer r, and B is the set of all integers n such that n is equal to 3s for some integer s. We wish to prove that A is a subset of B and disprove that B is a subset of A. Alright, so first, let's look at the A is a subset of B proof. So remember what we have to do is we pick an element. So suppose that x is some element in A. What we want to show is that x is also an element of B. Alright, so since x is an A, this means that there exists an integer r such that x is equal to 6r plus 12. But we can factor out a 3, and we'll be left with 2r plus 4. Where this 2r plus 4, right, it's a sum and product of integers, so it is itself an integer. Therefore, we just wrote x in the form of 3 times s for some integer s. Well, this means that x is in B, right? Right, because B is a set of integers that can be written as 3 times an integer. So therefore, A is indeed a subset of B. That is the element argument. Now to disprove that B is a subset of A, remember we want to find a counterexample. So B is a subset of A, our counterexample. Let x be equal to 3, which is clearly an element of B. We want to show that this is not an element of A. Suppose that it is. Right, so to prove that this is not an element of A, we'll use contradiction. Then there has to exist some integer r such that 3 is equal to 6r plus 12. Well, this means that 6r would be equal to negative 9, which would imply that r would be equal to negative 9 over 6, which is negative 3 over 2. So here we have r is an integer, and r is not an integer, right? Because negative 3 halves is not an integer. This is a clear contradiction. Therefore, x is not in A, which implies that B cannot be a subset of A. So given sets A and B, we say that A equals B, which is written as you would think A is equal to B, if and only if every element of A is in B and every element of B is in A. But if we think about this a little bit, right, if every element of A is in B, then doesn't this mean that A is a subset of B? And every element of B in A means that B is a subset of A. So in other words, we say that A is equal to B if and only if A is a subset of B and B is a subset of A. So this tells us how we can prove that two sets are equal. First, prove that one is a subset of the other, then prove the other way. So prove that they're subsets of each other. So we have two sets here. A is the set of all integers m, such that m is 2 times a for some integer a. The set B is the set of all integers n, such that n is 2b minus 2 for some integer b. And the question is, does a equal b? Well, this boils down to, is a subset of b and b a subset of a? And remember, this is not just a simple yes or no. It is if it is equal, prove. If it's not equal, provide a counterexample. Well, if we examine this, A is clearly the set of all even integers. Well, wouldn't B also be the set of even integers? Right? 2B is even minus even minus even is still even. So just looking at this seems to say, yes, these are the same. Well, that means I'm going to have to prove this. So let X be an element of A. then there exists an integer a such that x is equal to 2a. So we can say x is equal to 2a plus 2 minus 2. Right? All I'm doing here is I'm adding 0. This is a very common mathematical trick. Right? You just add 0. Well, now I can factor out a 2 from the first two terms, so I'm left with a plus 1 minus 2. But a plus 1 is an integer. So we just wrote x as 2 times an integer minus 2. Which means that s is in B, which means that A is a subset of B. Well, now, let x be in B. What we want to show is that x is in A. Right? So then, we have to have an integer B such that x is 2b minus 2. Right, but we can factor out that 2 and we're left with b minus 1, where b minus 1 is an integer. So therefore, we can write x as 2 times an integer a. I don't know why I'm writing that out. I want to write it out this way. Oops, on an x. A is an integer, which would mean that x is an element of A, which means that B is a set of A. Therefore, A is equal to B, right? Here we showed that A is a subset of B. Here we showed that B is a subset of A. So they must actually be the same set. So now we look at some set operations. So we let A and B be subsets of some universal set U. So whenever we talk about sets, typically there's some universal set. It's not always explicitly stated, it is usually implied. So for instance, if we talk about a set of integers, it's implied that we're talking about the set of all real numbers. It's a subset of the set of all real numbers. So our universal set would be real numbers. The union of A and B, which is denoted as this, is the set of all elements that are in at least one of A or B. The intersection of A and B, which is denoted as this, is the set of all elements that are common to both A and B. Now, I want to take a moment and examine these two. If you look at A union B, doesn't that kind of look like A or B, right? From logic. And it's even kind of defined the same way, right? A or B would mean that either A is true, or B is true, or both could be true. Whereas the union of two sets is the set of elements that are in one. So A union B would be the set of all elements that are in A, or in B, or in both. And the same thing here. Doesn't this kind of look like an and, right? So this kind of looks like A and B. Well, A and B from logic means, right, A is true and B is true. And look at the intersection. It's a set of all elements that are in A and in B. right? So the union and the intersection are very, what's the word I'm looking for? They're very similar. That's what I'm looking for. They're similar to or and from logic. Now we have a set difference, so the difference of B minus A, or the relative complement of A in B, which is denoted either this way, or more commonly in set theory, this way. And it is the set of all elements that are in B, but not in A. And then we have what's known as the complement of A, which is denoted as A to the C, or A bar. But again, in theory, it's more common to use A bar. And this is just a set of all elements that are in U, your universal set, but not in A. Now, probably the easiest way to visualize these four operations is by use of what's known as a Venn diagram. And I'm sure this is something that you're all familiar with. So let this box be the universal set. So let's say that's our set A. We'll say that this will be our set B. So if we're looking for A unioned with B, it's a set of everything that is in A or the set of everything that is in B. Right, so this would be our A union B. So it's everything that's in one of the two circles. So we again let this box represent the universal set, and let's draw two circles to represent our sets. We'll say there's A, here's B. If we're now looking for the intersection of A and B, it has to be the elements that are in both A and B. Well, that would just be this piece right here. We're now looking at B minus A. Let's do B minus A. And remember, B minus A is the set of all elements that are in B, but not in A. So just be what's in B, excluding what is in the intersection of A and B. And also what's in A. Right? So it would just be that. And finally, let's look at Okay, sorry, that is way too dark a color. Let's do yellow then. Let's look at A complement. So A complement is the set of everything in our universal set that's not in A. Well, we could have B minus A. However, we also have everything that's out here. Right? So it's literally just everything in the universe that is not in A. So let's take a look here. So we have a universal set, which is the set U, which is the set of A, B, C, D, E, F, G. A will be the set A, C, E, G, and B will be the set D, E, F, G. We need to find A union B, A intersect B, B minus A, and A complement. All right. So let's start with A union B. Well, remember, it's the set of all elements that are common to both A or B. So we look, it's all the elements in A and all the elements of B except any duplicates. So it'll be A, C, D, E, F, and G. A intersect B, remember, is the set of elements that are common to both of them. Well, A is not in B, C is not in D, E is in B, and so is G. So it's EG, the set EG. So B minus A is a set of everything in B except what's except what's in A. I'm sorry. So D is not in A. E is in A. F is not in A, and G is in A. So A minus B is the set DF. And finally, a complement is the set of everything in our universe except for what's in A. Right? So A is in A, B isn't, C is, D isn't, E is, F isn't, and G is. So A complement would be B, D, F. Well, in fact, we can take the union or intersection of more than just two sets, and we call these indexed collection of sets. So let's look at unions of an indexed collection of sets. And there are two possibilities. We can either have a finite union, so a union of a finite number of sets, or we can have an infinite union, a union of an infinite number of sets. So we have sets A naught, A1, so on and so forth. Each are subsets of some universal set U. And we also have a non-negative integer n. So first the finite union. So it'll be the union from I equals 0 to n, a sub I. This is the set of all x in the universe, such that x is in a sub I for at least one of 0, 1, n. So this means, what this is saying is that the union of I equals 0 to n of a sub I, right, is the set of all x, such that x appears in at least one of a0, a1, a2, up through an. The infinite union, so union of I equals 0 to infinity of a sub I, is equal to the set of all x in the universe, such that x is in a sub I for at least one non-negative I. So again, this is saying that it's the set of all x in our universe such that it appears in at least one of our infinite number of sets. Well, we also have intersections of an indexed collection of sets. So the intersection, and again, there's two of them. There's a finite and an infinite. So the intersection from I equals 0 to n of a sub I, this is the finite intersection, is a set of all x in U such that this is an a sub I for every I 0 to n. So this says it's the set of all elements in our universe that appear in every single a0, a1, a2 through an. Right now, the infinities, right? The intersection from I equals 0 to infinity of a sub I is equal to the set of x in U such that x is an ai for every non-negative I. So what this says is that our infinite intersection is the set of all elements in our universe that appear in every one of the infinite number of sets. So we're going to look at the two finite cases first, then we'll look at the two infinite cases. And we're going to use the same indexed collection of sets. So we're going to say that for every positive integer I, ai is the set of real numbers x, such that negative 1 over I is less than x, which is less than 1 over I. First, let's find the union of the first three a's and then the intersection of the first three a's. Well, ai, another way of writing this is a sub I is equal to the interval negative 1 over I to positive 1 over I. So using this, we can say that a1 is the open interval minus 1 to 1. A2 is the open interval minus a half to a half. And A3 is the open interval minus a third to a third. Now if we look at this, negative a third to positive a third would be contained within the interval minus a half to a half. But this itself would be contained entirely in the interval minus 1 to 1. So we can say that the union from I equals 1 to 3 of a sub I would be the entire interval negative 1 to 1. Right? Because that interval contains all of negative a half to a half and all of negative a third to a third. However, the intersection from I equals 1 to 3, remember this has to be the set of all elements common to everything. Well, since negative 1 to 1 has negative a third to a third, and so does negative a half to a half, this intersection would be negative a third to 1/3. Now let's look at the infinite case. So we can use the same argument as before, right? We're just going to extend it, right? So a sub I, again, is the interval, I'm sorry, negative 1 over I to positive 1 over I. And also notice that a sub I will converge as I approaches infinity to just the set 0. Right? Both of these, as I goes to infinity, go to 0. And so x would go to 0. So it's only 0. Well, using this now, the infinite union, I equals 1 to infinity, of A sub I? Well, once again, right, it's going to be -1 to 1, then -1/2 to 1/2, then -1/3 to 1/3, -1/4, right? But -1 to 1 is going to contain everything. So that is our infinite union. Our infinite intersection, however, if we look at the sets, the only thing all of these will have in common is 0. So we say that sets are disjoint if and only if they have no elements in common. That is, two sets are disjoint if and only if A intersect B is the empty set. So this represents the empty set. You can also represent just simply an empty pair of braces. And the empty set is the set that has no elements, obviously. So we say that sets A1, A2, so on and so forth are mutually disjoint or pairwise disjoint if and only if no two sets, AI and AJ, with distinct subscripts have any elements in common. That is, if and only if the intersection of A sub I and A sub J is the empty set whenever I is not equal to J. So we have three sets here. We have A1 is the set 3, 5, A2 is the set 1, 4, 6, and A3 is the set 2. And the question is, are A1, A2, and A3 mutually disjoint? So we have to determine whether each pair of intersections are empty. So A1, A2 does not have 3, A2 does not have 5, so that's empty. I should be careful, that looks like a Greek letter. Let's do it that way. There we go. Now look at A1 with A3. Well, A3 does not have 3, A3 does not have 5, so that is also empty. And now look at 2 with A3. Right? A2 does not have 2, and so that is also empty. So therefore, these three sets, A1, A2, and A3, are mutually disjoint. So now let's look at these three sets. So B1 is the set 2, 4, 6, B2 is the set 3, 7, and B3 is the set 4, 5. Are these mutually disjoint? So again, we want to check to see if each intersection is empty. So B1 intersected with B2, right? So 2 is not in B2, 4 is not in B2, 6 is not in B2. So that's empty. B1 intersect with B3. So 2 is not in B3, 4 is, and 6 is not. So B1 intersect B3 is not empty. And that's all it takes is for one intersection pair to not be empty. Therefore, these three sets, B1, B2, and B3, are not mutually disjoint. So now we look at what's known as a partition of sets. So a finite or infinite collection of non-empty sets, A1, A2, so on and so forth, is a partition of a set A, if and only if A is the union of all the AIs, and the sets A1, A2, so on and so forth are mutually disjoint. So let's define Ti to be the set of all integers n such that n is equal to 3k plus I. The question is this a partition of the integers? So to determine whether this is a partition, let's take note that T1 will be the set of all integers n such that n is equal to 3k plus 1 for some integer k. T2 is equal to the set of all integers n, and I'm sorry, in T1 I shouldn't have used this such that symbol, I should have used the vertical bar, such that n is equal to 3k plus 2 for some integer k, and T3 is set of all integers n such that n is 3k plus 3 for all integers, or for some integer k. Now we can rewrite T3 as the set of all integers n such that n is equal to 3 times k plus 1 for some integer k, right? Which is the same as saying 3 times an integer. Well, by the quotient remainder theorem, remember that? For all integers n, there exist integers q and r such that n is equal to 3q plus r and 0 is less than or equal to r less than 3. Well, the only integers between 0 and 3 are 0, 1, and 2. Well, if we look up at here, right, this is 3 times some integer q plus 0. Right, in this case, the integer is k plus 1. So this covers where the remainder is 1, that's T1. T2 covers where the remainder is 2. And T3 will cover where the remainder is 0. So, and they're all disjoint. So T1, T2, and T3 do form a partition of the set of integers. Now, if we're given a set A, the power set of A, which is put as the script P of A, is the set of all subsets of A. So we're going to find the power set of the set X, Y. So first list out the subsets of the set X, Y. Well, we will prove later that the empty set is a subset of every set. So we're going to have the empty set, the set X, the set Y, and then the set X and Y. So our power set of the set XY is the set of the empty set, the set of X, the set of Y, and the set of X and Y. So now let's look at some subset relations. First, it's known as the inclusion of intersection, and it says that for all sets A and B, A intersect B is a subset of A, and A intersect B is a subset of B. Next is the inclusion and union, which states that for all sets A and B, A is a subset of A union B, and B is a subset of A union B. Then we have the transitive property of subsets, which states that for all sets A and C, if A is a subset of B and B is a subset of C, then A is a subset of C. Now, the proof for each of these three relations is a simple matter of applying the element argument, and this will be left to the viewer. Now we look at set identities, or set properties. So, let all sets referred to below be subsets of the same universal set U. First are the commutative laws. For all sets A and B, A union with B is equal to B union with A, and A intersect with B is equal to B intersect with A. So the order in which you do union and intersection does not matter. Next we have the associative laws, which states that for all sets A, B, and C, A union B quantity union with C is A union with quantity B union C, and the quantity A intersect B intersect C is equal to A intersect the quantity B intersect C. So how you group unions and intersections does not matter. The third is the distributive laws, and this states that for all sets A, B, and C, A union with the quantity B intersect C is A union B quantity intersect with A union C quantity, and A intersect the quantity B union C is equal to the quantity of A intersect B unioned with the quantity of A intersect C. So union distributes across intersections, and intersection distributes across union. The identity laws for every set A unioned with the empty set is A, and A intersected with the universal set is A. The complement laws for every set A unioned with A complement is the universal set, and A intersect with A complement is the empty set. The double complement law for every set A complement is A. The idempotent laws for every set A union with itself is A, and A intersected with itself is A. The universal bound laws for every set A unioned with the universal set is A, and A intersected with the empty set is the empty set. And I apologize, this here should not be A. That should be the universal set. So A union with the universal set is the universal set. De Morgan's laws for all sets A and B. The complement of A union B is the complement of A intersected with the complement of B, and the complement of A intersect B is the complement of A unioned with the complement of B. The absorption laws for all sets A and B. A unioned with the quantity of A intersect B is just A, and A intersected with the quantity of A union B is just A. The complements of the universal and the empty set. So the complement of the universal is the empty set, and the complement of the empty set is the universal. And finally, set difference for all sets A and B. A minus B is the intersection of A and the complement of B. So we will now look at proving some of these. So first, the proof that A union with the quantity of B intersect C is equal to the quantity of A union B intersected with the quantity of A union C. So first you have to suppose that A, B, and C are arbitrary sets. Now let's suppose that X is in A unioned with B intersect C. Then X is in A, or X is in B intersect C. If X is in A, then X must also be in A union B. Also, X must be in A union C. So X would be in both, which means that it is in the intersection of A union B with A union C. Now, if X is in B intersect C, then X would be in B and also in C. Since it's in B, it must be in A union B, and since it's in C, it must be in A union C. So it's in both, which means that X is in the intersection of A union B with A C. Thus, in either case, if X is in A union with B intersect C, then X is in A union B intersect with A union C, and thus you have this being a subset of this. Now we just have to go the other way. So now suppose that X is in A union B intersected with A union C. Then this means that X is in A union B and X is in A union C. If X is in A, then it's got to be in A union with B intersect C. If X is not in A, then X is in B, since it's in A union B. Also, X must be in C, since X is in A union C. Thus, X would be in the intersection of B and C, and thus X would be in the union of A with B intersects C. So in both cases, if X is in the intersection of A union B and A union C, then X must be in A union with B intersects C, and therefore this is a subset of this. Well, that shows both directions of subsets, so we can conclude that they must be equal, and the proof is complete. So now let's go ahead and prove that the complement of A union B is the complement of A intersected with the complement of B. So again, first suppose that A and B are arbitrary sets. Now suppose first that X is an element of the complement of A union B. Then this means that X cannot be in A union B, which means X is not in either A nor B. So X would be in A complement and X would be in B complement. So X would be in A complement intersected with B complement, and hence this set is a subset of this set. Now let's suppose that X is an element of A complement intersected with B complement. Then X is in A complement and X is in B complement, which means X is not in A and X is not in B. So it's in neither X nor B. So X is not in A union B, which means it must be in the complement of A union B. Therefore, this set is a subset of this set. Well, that means that they must be equal. And so the proof is complete. Now, for any sets A and B, if A is a subset of B and A intersect B is A, then A union B is B. So let A and B be arbitrary sets such that A is a subset of B. If x is in A intersect B, then x must be in A. Thus, A intersect B is a subset of A. If x is in A, then x must be in B, because A is a subset of B. So again, x is in A intersect B, which means A is a subset of A intersect B. So A intersect B must be equal to A. Now, if x is in A union B, then x is in B, which means that x is in A union B. Which means that A union B is a subset of B. If x is in B, then it must be in the union of A and B, and so B would be a subset of A union B, and hence A union B is equal to B. And that proves both statements of the theorem, so the proof is complete. Here's where I promised we would prove that the empty set is a subset of every set. So if E is a set with no elements and A is any set, then E is a subset of A. Well, we're going to have to do this by contradiction. So suppose there exists a set E with no elements and a set A such that E is not a subset of A. Then there would exist an X in E such that X is not in A. But that's a contradiction, because E has no elements. So we're saying that there is an element in E, but also there are no elements in E. And so our original supposition is incorrect, and E must be a subset of A. Now, as a corollary of this, we can prove that there's actually only one set with no elements, which is why we call it the empty set. So suppose that there are two sets, E1 and E2, both with no elements. Well, then by the previous theorem, E1 must be a subset of E2. However, also by the previous theorem, E2 must be a subset of E1. Hence, they're actually the same set, and the proof is complete. We can now prove that A intersected with the empty set is the empty set. So let A be a particular set. Suppose that there exists an X such that X is in A intersect with the empty set. Then X would be in A, and X would be in the empty set. But this is saying that X is in a set with no elements. That is a contradiction. Hence, A intersect the empty set is the empty set. So what this example is doing is it's showing you how to prove that a set is empty. You always do it by contradiction, and you assume that it is not empty. All right, so proposition. For all sets A, B, and C, such that A is a subset of B, and B is a subset of C complement, then A intersects C is the empty set. Well, we're going to do this by contradiction. Suppose A, B, and C are arbitrary sets such that A is a subset of B and B is a subset of C complement. Also suppose that there is an X in A intersects C. Then this would mean that X is in A and X is in C. However, since A is a subset of B, and since B is a subset of C complement, then A is a subset of C complement by transitivity. Thus, X is in C complement. Well, this is saying then that X is in C, but also in the complement of C. Well, this is a contradiction. It cannot be in both. Hence, the intersection of A and C must be empty, and the proof is complete. So that concludes our study of sets, and that also finishes our unit of sequences and sets. So in the next video, we are going to begin our next unit, which is relations and functions.